Good day, Graham Hillstrand, CEO, Embedded Systems Technology. Welcome back to part 2 of this four-part presentation and video on model-based design of mobile cyber-physical systems. We're interested in conceiving and engineering safe mobile systems and systems of systems, and this requires an ecosystem of partners in order to be able to do this effectively. So what is part 2 going to cover? The modeling and simulation of subsystems and systems using the ESSE workbench. So we'll be developing a golden reference model, translating that abstract control to operational controllers running real software, modeling and simulating subsystems and systems, and we'll see a little video of a simulation of that, and then the ESSE workbench in use. Here is our context, which is the same as for part 1, which you may remember. Connected automotive cyber-physical systems of systems, a car in detail, plant, engine, control for that plant, and ECU running software, networked with the transmission, networked with suspension, networked with braking, etc., and the 30 ECUs that might go across 5 networks to make up the real-time control system within the vehicle. Outside of the vehicle we have radar, perhaps infrared, perhaps video. We might also have mobile Wi-Fi, the so-called dedicated short-range communication, or DSRC, to allow these vehicles to communicate with each other and coordinate their activity, including autonomous activity. So that's the context. So let's have a look at developing mathematical golden reference models, or the so-called executable specifications. We might start off by having a look at a combined plant and control model, which is how the powertrain engineers do this. Differential equations or differential algebraic equations. Sometimes these may be finite state machine together with some continuous domain models, so data flow, state flow type models. Connected to sensors so that you can observe what's happening here, and to actuators to allow an external stimuli to change state with these abstract models. The next step would be to begin to differentiate the plant model from what will become the control model, and you can see that here in green. So we're factoring out the differential equations that might specify control from the plant models that might specify what the plant is doing. We still need to be able to control the plant model from the controller model. We may need to synchronize this with external stimuli to get actuators that change the state of the plant model, and then to sense what the change of state was by having sensors sitting there which we can read. Again, we synchronize in order to get the same data at the external output and the feedback to the feedback control loop for the controller. So that's a differentiated plant from control in an abstract model. We might have a slightly more complex version of this, where we might have an engine and a transmission. These things are coupled mechanically by a drive shaft. We would represent that by perhaps the engine model here in terms of a continuous domain differential equation model, perhaps a continuous domain differential equation model of transmission. Here's the mechanical connection. Perhaps we've differentiated control for the transmission, control for the engine. And now we're synchronizing 3 sources of input into the actuators that are going to drive each of these models at the same time. And we're sensing the state change within those models using sensors, which again being driven back into the feedback control loop of the 2 controllers. And we can see what's happening at the same time in external stimuli. We can now put this in a network, and that network might be connected with high-performance, accurate models of, say, a CAN network or a FlexRay network. In our case, we use the ESSE SNF-derived CAN and FlexRay networks, which are very high-performance, bit accurate, and timing accurate. Coupling these models in then builds a distributed real-time control system where each of the controllers is communicating with the element it's trying to coordinate with via, in this case, CAN messages or FlexRay messages. So this forms the distributed control system of a vehicle. So let's plug it into a vehicle dynamics model. And here we're perhaps replacing some of the simple models in a typical vehicle dynamics model with a accurate model, a high performance accurate model, and the connections between those we're replacing as well in the vehicle dynamics model. So we're plugging these accurate models into the relatively less accurate vehicle dynamics model. So moving on from there, we can do this with all of the elements in the vehicle, all the plant and all the control, and we'll end up with a network abstract model, a golden reference model, that entire vehicle, which we can use in order to specify what the physical model might look like, and we can use it in order to compare what the operational model in terms of real software and models of electronic control units executing that software. Let's move on to that. So here we are going from a golden reference model to the operational model. Here are our golden reference models. We're now interested in the control part of that, either translating that to a state machine or translating that to software, and that translation may be automatic, that will run on some sort of microcontroller unit or an expanded version of that, an electronic control unit. We'll call these things virtual ECUs. Here is an engine model, maybe Simulink, a differential equation and finite state machine, connected mechanically to a transmission model. We have a controller here for the engine, software running on an NEC V850E2, various peripheral devices on a bus connected to a CAN controller. The transmission controller is much the same, except our software is running on an Infineon Tricore. We might have the brake and suspension units on another network, in this case a FlexRay network, and these two networks bridged with an active controller so that network messages can be translated back and forth between those two systems. So we've essentially taken this abstract control, converted it either to a finite state machine or software running on an MCU. So we've generated here our operational control units. What I'd like to show now is a simulation of this system. So I'm going to show the engine model running in a simulation, and that simulation is actually of two cars running together. So here we saw the tool from SimuQuest called Ingenuity, which is generating an engine model. It generates in Simulink, so MathWorks is involved here too. We see the various elements of the engine model. We have gauges that we're looking at. At this point, we're looking also at details from the engine and details from the vehicle. You'll see here vehicle speed, active gear changing, torque from the engine, engine speed, manifold pressure, air mass flow, etc. So very detailed calculations coming from that vehicle model. So we're getting an awful amount of information from these models, which are very accurate. And that's precisely what we're interested in seeing. Let's duck across and have a look at what's happening in the larger simulation. So in the larger simulation, we're going to see a couple of cars running around. So here we come with the what we actually did in the simulation. Two cars, blue car following the red car, going up the straight line, turning around a curve, and stopping. And we were doing those calculations that you see over in this part of the screen exactly from that simulation. So let me just jump up here a little bit. What I'm interested in now is having a look at some of the details of the gases produced here. So I'm interested in the instantaneous output of carbon monoxide, carbon dioxide, and nitrous oxide. So that's exactly what we're seeing here. We'll see a little more detail of these calculations. So you can see that we're getting a lot of information there. Let's also look at the instantaneous, or the aggregate, output of carbon monoxide, carbon dioxide, and nitrous oxide, the total amount produced by a single run of that simulation that we saw. And let's do the same thing for fuel consumption. So here's the instantaneous fuel consumption. We get more detail of that. And let's look at the aggregate fuel consumption for this vehicle. So there's the aggregate fuel consumption. You can see the total amount of fuel that's been consumed there. So we'll go back to our presentation. So you can see there we're looking pretty much at details of the engine model. We're also tracking the vehicle here. We're tracking gear changes, we're tracking vehicle speed, and we're tracking braking and deceleration. So we're seeing not just this part of the real-time control system, but we're also seeing part of the vehicle dynamics model as well. So here's a report of an exercise we ran with one of our customers, a global OEM, producing a high-performance full vehicle plant and control model that achieved remarkable accuracy with respect to the physical vehicle that it was controlling. So here is the characteristics of what we did here. As I mentioned, the vehicle, we had powertrain regenerative braking. We had the ECUs connected to the powertrain models and the braking models. We're running production software on the controls for the engine. Software editors, compilers, and debuggers running, with the debuggers running on a couple of those ECUs. The final vehicle model had all the subsystems integrated into it and driven through this standard 1015 test and simulated using the ESSE workbench. And this simulation ran across 6 Intel x86 cores and achieved about 10 times real time to a 10th real time, depending which detail of models it was using. The 10 times from the abstract models and the 1/10 from the very detailed operational models of the ECUs. So this is what was happening in the ESSE workbench. We had a full vehicle control system development going on, concurrent development, verification, and proving. Here's our golden reference model, complete vehicle. The operational models being converted and the software either being generated or being converted. We can now compare these two models directly, both in function and timing. And we can start to report differences. And those differences will indicate that where the operational model diverges from the golden reference model. That means the operational models aren't meeting specification with respect to either timing or function or both, and they need to be corrected. The other thing we can do here is not just do this concurrent verification with development, but we can also plug in the golden reference model with vehicle dynamics model, which we saw in a previous simulation. But we can also do the same thing with this operational model, plug it into another vehicle dynamics model, and see how both cars behave side by side. And that usually gives a very good visual perspective to the engineers to see what's happening and what's not happening correctly. So that's highly motivating to the engineering team to be able to get that visualization, as well as the rest of the data from the plant and from the controller models. So let's summarize what we saw in part 2 of this 4-part video presentation and sequence. We represented subsystems and systems in terms of abstract mathematical models. We converted those to operational derived models of the control. We had an advanced model development process to allow us to do that, and we stepped through that. And we saw the ESSE workbench in use, and we saw a motivating video of 2 cars being simulated and recording instantaneous emissions and fuel consumption and aggregate emissions and fuel consumption during that entire run. So thank you very much for your attention during this part 2 series. We invite you back to view part 3 and look forward to seeing you there.